Let f of xy be equal to x cubed plus y cubed plus 3xy for all real x and y. Then there exist distinct points p and q such that f has a local maximum at p and q, a saddle point at p and q, a local maximum at p and saddle point at q, minimum p, saddle point at q, and minimum at p and q. Interesting. Okay, so we're essentially just being tested whether we know the conditions for a critical point of a function to be a minimum, maximum, or saddle point. I'll have to remember myself what those are. We'll have to take, it involves the determinant of a matrix. Let's first start by computing some partial derivatives. So I have my function. So critical points correspond to partial derivatives being equal to 0. I'm happy they chose the function so that this will be fairly straightforward. So if I solve for both of these equal to 0, oh, made a mistake here. So I have x squared plus y is equal to 0, and y squared plus x is equal to 0. Okay, so 0, 0 is one of the solutions here. X and y are both real. So of course, if I write this as x squared is equal to negative y, and y squared is equal to negative x, for these to have solutions, both x and y have to be negative. And then it's pretty clear also that another solution to this will be x and y are both equal to negative 1. Okay, so there's the other critical point. Now we need to figure out if these are saddle points, minima, maxima, and all that. Without computing more derivatives, I wonder if there's a quick way of seeing this. So if I think about the origin around 0, I look at this function. I'm not positive here. I think I might just go ahead and compute the appropriate second derivatives and do the second derivative test. Okay, so I need second derivative, which is 6x, second derivative in y is equal to 6y, and the mixed derivative is equal to 3. So the matrix I need here is 3x, 3y, 3, and 3. I need to take a determinant of this, and that is 9xy minus 9. Okay, so, and then I need to substitute in my 2 points here. Okay, so when x and y are both equal to 0, let's call this matrix H. then the determinant of h is -9, and this means we have a saddle point. And when x and y are both equal to -1, the determinant of h is 0. Uh-oh. So 0 means it's inconclusive, right? Well, it's neither. It's certainly when x and y are both equal to 0, we certainly don't have a minimum or maximum, right? If I let y be equal to 0, so we just ignore this, then we have x cubed. So it's neither a minimum nor maximum because the value of the function is 0. I can make it slightly positive or slightly negative by changing x a little bit. So at 0, oh, we've already determined that though, that it's a saddle point. But what about at -1? Make sure I did this all correctly. Uh-oh, no I didn't. I substituted these things in. I made a mistake here. Okay, so when it's equal to -1, we have 27. And this implies it's a min or max. We don't really know exactly what it is, but what we can do is just think of this as a function of one variable where I let x equal -1. So I have x cubed -1 minus 3x. Well, or just, no, let's do it the easy way. Let's look at the second derivative in the x direction. It's negative, and so this gives us a maximum. Okay, so here's our answer. We have one saddle point and we have one maximum, local maximum. So the answer is C. Yeah. Stumbled through this one a little bit. It wasn't super bad in the end, but you know, I had to refresh my memory on a little bit on exactly how to verify that a critical point of a multivariate function is a minimum or maximum. Yeah, but I guess the first key here was actually finding what the critical points are. That required a little bit of work. One of them is really easy to find, 0, 0. And the other one at -1, -1, well, recognizing we're only going to get a solution here when both x and y are negative, that kind of helped. And then what else? Yeah, remembering the classification of optima or saddle points is something that you know, I've never really used very often, but I just kind of remembered what the classification is, right? The determinant of this matrix of second derivatives can be positive, negative, or 0. I know that positive is the good case, negative is the saddle point case, and 0 is indeterminate. It just doesn't give a conclusion. But it turns out that that's all we needed because one of the outcomes was negative and one was positive. If I have more to say about this one, I'll put it down in the description. Thanks for watching.